Hey everyone, let's now talk about another concept that is important in math for vectors, and that is the dot product. You probably remember it from school, or probably not, but you at least heard of it. So basically what it does is it describes the relationship between two vectors to each other. And it's actually quite simple. Let's say we have two vectors, the orange one and the white one behind it, there it is. So if we want to calculate how the two relate to each other, we can use the dot product. And it's simple to remember. If they are exactly on top of each other, then the dot product is 1. If they are perfectly 90 degrees to each other in any direction, by the way, for example, this one as well, then the dot product is exactly 0. And if they're the complete opposite to each other, they're -1. So that means everything in between is between those extremes. So -1, 0, and 1, and that then describes the relationship between the two. Now the numbers are not linear, so something here in between is not exactly 0.5, so maybe 45 degrees. You will not get 0.5, so doesn't work like that, but it's a good way of just calculating the general relationship. So what can we do with that? First of all, the way to use that is relatively simple, and that is the command is of course simply dot. So let's say we wanted to do something that we actually can do in other ways, but let's say we want to use the normals of the sphere and delete everything that doesn't point upwards. The command we use is called dot, and of course this is run between two vectors. And the first one is the normal of the sphere that we already have. I calculated with a normal node, and then we define a random vector, let's say an upwards vector of 0, 1, 0, for example. And let's save the result of this into an attribute called dot. And what we can see here now, there it is, that we have all kinds of dot products between 1 and -1. And that of course is because we have, all kinds of directions. Now, what do we do with this? Well, for example, we could say, okay, everything that is not at least somewhat pointing upwards should be deleted. So let's say if the dot product is less than, let's say 0, and remember 0 would be exactly 90 degrees, -1 would be the complete opposite. So 0, smaller than 0, basically means everything in the hemisphere of 180 degrees. And if that's the case, if it's less than 0, then just remove the current point of the sphere. And there you have it. This way we can, delete stuff based on an angle. And of course we can change the dot product by, for example, adding it to a parameter. So let's call this dot threshold or something. And then we can play around with this more naturally and can say, okay, it has to really point upwards to survive. And currently we don't have the option to have a negative number. Let's change this. There we go. Or we can say, okay, if it's completely the opposite, then delete it. So of course, this is not really impressive because we already know how to do this. We can do the same thing with the group, for example. So the group has the function of exactly that, filtering for the normal direction. And internally, by the way, this is exactly what this is using, the dot product. So we just rebuild this function here with our own VEX code, so you can integrate it maybe into a bigger VEX project. There's also another node that does the same thing, and that is mask by feature. Because if you remember, you can actually also define here the direction, and here's the mask. Internally, again, it uses actually a dot product, even though it might not seem like it. So this is nothing really new per se, but we now know how to do it in VEX, and that is the dot product. What you can do with this, of course, is, for example, we could use something more complex. And as we've seen before, we can use our code here to delete everything that is not pointing upwards. Let's be a bit more aggressive. And then we just scatter on this, and we can create some kind of, snow generator or something like that, which we've done before, but this time at least we've done it with VEX ourselves. Now, one thing to keep in mind, and this is why I put this big green box here, always remember that the vectors you do this with should be normalized. So if we look at our example here, we didn't care about this because we were lucky that the normal by definition is always normalized. And then we defined a vector that is also normalized because it has a length of exactly 1. So this time we were just lucky. But for now on, let's keep that in mind that we always have to normalize our directions. because we want to look now at a more interesting example. And that is, let's say we want to create some kind of angle-based scatter system, which is very similar to what we just saw, but this time we don't want to define a vector by typing it in. But let's say this here is our sun or something, and we want to stuff only grow in the direction the sun is pointing. I don't know why you would do that, but it's something that looks interesting and we can do with the dot product. So here, as you can see, the moss, which is just points that I'm scattering, are always pointing towards or only emitting if the angle of the normals of the particular geometry is pointing in that direction. So how do we do this? So let's start with a fresh example, and we create a point wrangle, and what we want is on the scene that I have here, we want to create an attribute that we then use in a scatter to define where we allow to scatter, basically. So of course what we need is, and by the way, the sun is in the second input, so let's move it over here, and the function is dot. So what do we want to create the dot product from? Well, first of all, we need the normals. That's easy, that's already in Vn. And then we need somehow the direction to the sun. So I call this dir to sun, maybe. So this should be a vector. And the direction to the sun, you should actually know how to do this, because we've done this before. How can you calculate from the current position on any point of our landscape the vector to my sun? Of course, we will use the min-pos, because we want to find the closest position on the surface of our sun. So the direction to our sun is my current position minus the position on the sun. And this is something we can calculate via the min-pos of the second input, because that's where my sun is in, and then relative to the current position. So what we calculate here, of course, is a vector between my point and the end point. And we can quickly check this by just putting this onto an attribute just to see what we did here. And there's an error because the dot, so let's comment this out for now. And let's see how this looks like. And my point here is just we should get used to always check what we're doing and don't assume anything. Don't assume that you were right, because that's usually a bad idea. Always check what's happening. And I kind of knew that this would happen, but I did it anyway. As usual, I mixed up the direction. So it should have been P2 minus my position. And I could instantly see that because the vectors were correct, but in the wrong direction. There you go. And another thing I can see is that the vector, of course, is the whole length between the 2 points. But I know I will need this for the dot product anyway, but in general, it's a good idea to normalize a vector like this, because it's supposed to only be a direction. I don't care about the length really. And then you can see I have the right direction, but it has the length of exactly 1. So that seems to work. We've done this before. All we have to do now is, and we don't need our visualizer anymore, we just take this direction. We don't need this attribute either. We take this direction and put it into our dot, and let's put this into our dot attribute, for example. And I forgot the semicolon at the end. There you go. So let's visualize this. There is the dot product. And if I show this, you can see, oh, that looks promising. So it shows it as a color, and that is totally fine. And yeah, seems like it's working. All we have to do now is we have to use this for our scatter. So you might change the name to scatter or something, but I'm too lazy. So I use scatter and just use my density attribute dot, because why not? And then I turn off my relax iterations so I can really push the numbers without too much of a speed problem. And then I increase this, and here you can see what's happening. And by the way, I still have my dot product visible. So here we go. This is basically the idea. Let's give it some stupid color. There you go. And merge it with the original, and then we are done. So the really hardest part here was to calculate the direction towards the sun, and this is something we talked about in another video before, and that is min-pos and working with vectors. And there you go, that's it. And you know, feel free to come up with better ideas what to do with this, but overall it's all about finding directions relative to something else. And I want to show you another example what you could do with this. One could be, here I have a circle. so ignore the end result, and I'm calculating the normals that are going outwards. And let's say I want to figure out if an object is in the field of view, so to say, of this curve. So roughly it would look like this. How can I calculate this? Well, I could take my object, the sphere for example, and calculate how it relates to the normals. So what I calculate is for each point the angle towards the surface, and then calculate how this relates to the normal of the curve. So the code looks like this. First I calculate the closest point normal, and then also the position, and calculate the direction between the point and the curve, and compare this with the normal of that curve. And the result of this looks like this. If you look carefully, if I move my sphere now in the angle of this, in all degrees, by the way, because a dot product doesn't care what direction the angle is, I can calculate if a sphere is kind of, let's call it, visible by this area or not. And of course I have to adjust a little bit the dot product itself. So here maybe 9.8 or something, so that's exactly in the direction would be better, so to make it more aggressive, or maybe even more than that. There you go, and maybe even more than that. Yeah, now it's really aggressive. And now you can see that it really the points only get red when they're really in the visible area of the normals of this curve. Now this could be interesting for all kinds of stuff, and of course there are other ways of doing this, but an angle-based check for this is certainly an interesting way of solving this problem. What you can see on this example is actually, by the way, something the dot product is also used in, and that is video games. So when you ever had a video game where the angle of view was important of an enemy, for example, then what was used here was actually the dot product to calculate the dot product between the view direction and the position of your player, to calculate that in a very quick way. So that's the advantage of a dot product. It's a quick calculation. And then finally, to finish this off, there's an interesting concept that I actually saw in a forum, and I loved it so much that I want to share it with you. Keep in mind that a dot product doesn't necessarily only work with directions. It works with vectors. And color is also a vector. Why is that cool? Because we can check if a certain color is in the same direction of another color. What do I mean by that? What I did here is just used an attribute noise to create random colors on the sphere. And now I can calculate the dot product of this current color, make sure that we normalize it, like we said before, and then normalize a vector that we define ourselves, maybe call it compare color or something like that. And what comes out of this is of course a float. And if that float number is smaller than a certain threshold, 0.5 or something, then remove the current point. So what did we do with that? So first of all, let's define our compare color, and I can quickly do this, and I'm sure there's a more intelligent way than just creating a color vector and then switching it to color. I think there is a better way of doing this, but never mind. And I say, let's say I choose something that is blue, and with a threshold I can now define everything that is in the kind of bluish, so to say, should be deleted. Or actually, if it's not bluish, let's say the other way around, if it's bluish, it should be deleted. So if it's higher than the threshold, so in other words, it goes in the same direction, or it is more or less the same color, then I can delete everything that is lower than this number. And you can see I delete first the bluish area before everything else goes away, because the direction of blue, so to say, is the same to another blue color, if that makes sense. So I found this really fascinating. So what can you do with that? For example, let's say we have an attribute map, for example, and we want to, filter out everything that is blue, for example, on this world map here. Then we can do this with our system, which is the same as we just wrote, just call it dot threshold, and then you can delete all the blue water areas, boom, and what's left is only the world without water. And it just shows how powerful the dot product is if you give it some attention. So yeah, so that's the idea behind the dot product. It calculates the relationship between two vectors. If they are in the same direction, the result is 1. If they're 90 degrees to each other, the result is 0. And if they're complete opposite to each other, they're -1. And this means you can check certain directions relative to some other vector that you calculate, and can check for all kinds of things. For example, how the normal is related to the direction to our sun here, so that you can create an attribute only pointing towards the sun, for example. Keep in mind, whenever you use the dot product, you should normalize your vectors. So just make it a habit, even if you know that you don't have to, add normalize before the vector that you put in, and then you can be sure that the result will be correct. Otherwise, you might get weird results. So that's the dot product. I hope this is helpful. Thanks very much and see you later. Cheers.